Hello everyone. So we're going to continue on the Josephus problem. Last time we proved that j2 to the power of m plus l is equal to 2l plus 1. And when l is the remainder of representing of certain number to a 2 to the power of m. We can expand that expression into more generalized forms, considering the case where every n can be represented as radix 2. So for example, when n is equal to radix 2 representation of n, we have all the coefficients for the 2 to the power of 2 to the powers. We can represent it as bm minus 1 dot 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 b1 b0, and in the subscript we can tell 2, which indicates that it's a radix 2 representation of n. This by expansion is exactly the same as n is equal to bm times 2 to the power of m plus bm minus 1 times 2 to the power of m minus 1 dot 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 all the way down to b0, where there is no power of 2. Well, exactly 2 to the power of 0, which is 1. So basically bi is either 0 or 1, and where the leading bit bm is 1. Another interesting question we can prove, aside from this, where this doesn't explain, is can every natural number be represented as radix 2, right? And uniquely represented, or is it not unique? Something to ask ourselves. So is every n representable? If so, is the solution unique? This is something to keep in mind and enlighten ourselves if we like to prove that these answer ourselves these questions. But this is a topic for another time, where we just want to prove that, discover something really amazing here. So when n is equal to basically where bm should be 1, so this is a radix representation for n, and the l is the remainder where all the coefficients for 2 to the power of m minus 1 down to 0. So bm should be with 0. And 2l is basically you have apply everything by 2. So the the b0 is going to be the coefficient for 2. Now the coefficient for non power of 0 is going to be 0. 2 to the power of 0 is going to be 0. And if you add them together, 2l plus 1, you get basically everything by bm minus 1 all the way down to b0, then 1, because you b0 plus 0 is let me just double check. 2l plus 1 is basically bm minus 1, 2 to the power of m minus 1. Oh, sorry. So 2l plus 1 is basically 2l plus 1. So the zero, at the 0th place, it's going to be added by 1. So it's going to be 1. Jn is now, what you need to consider in mind is the thing we proved last time is Jn is equal to 2l plus 1. So here we have 1. 1 is equal to basically bm. So dot 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 b1 b0 bm. So you can see that when n is represented by radix 2, what you can consider Jn to be is move the Bm all the way to the 0th place, and everything will be switched over one side to the left and switching their places. So notice that Bm minus 1 is now the leading one, Bm being the last one. So the last step follows because 2Jn equal 2L plus 1, and because Bm is equal to 1. We have proved that when input of the radix representation is passed into Josephus function, what happens is that coefficient of the Bm minus 1 is going to be switched every place of coefficients is going to be switched over to the left, and the first one is going to the tail. So which is amazing in terms of when we look at this in terms of radix 2 representation.